Okay, so now we're going to look at question 3. And they're saying, find I0 by making successive appropriate source transformation. The first thing is to understand where I0 is. I0 is here. Once you understand the element you're trying to analyze, that element must be isolated. It must not be tampered with as you make the transformations. Now, what happens during source transformation? Source transformation is actually very easy. And if you find this in a test or an exam, this must be among the questions you want to work out, because if you know how to deploy it, it's very straightforward. You keep using the same formula throughout in source transformation, which is Ohm's law. Voltage is equals to current times resistance. But how does it work? In source transformation, you should understand to say that if you have a voltage source connected in series with a resistor, so if this is a voltage source V supply connected in series with a resistor R here, according to source transformation, you can actually transform this resistor and voltage source. Let me do it somewhere more visible. Okay, so according to source transformation, if you have a resistor and a voltage source connected in series, like the way these two are, so that this is node A and this is node B, you can transform this so that you now present it as a current source instead. Now the current source will be connected in parallel to the same resistor. So to the same resistor, if this is R, this will also be R. This is R1, this will also be R1. And then the nodes A and B will be here. But what will be the current source that will now be here, IS? These will be connected by Ohm's law. Voltage S will be equals to IS multiplying R1. So if we wanted to find IS here, easy. IS will be equals to VS over R1. So that is how it goes. In the same way, if what you have is a current source connected in parallel to a resistor, in the same way, we can easily transform this by using Vs is equals to Is times R1, so that now we present it as a voltage source connected in series with the same resistor R1, and then the nodes A and B. We quickly see that it's the same concept we keep deploying, and it's basically one equation. So here, this has to be one of the easy concepts that you're going to look at in this course. So with that in mind, let's see how we can use this in our circuit. So this is the problem we're trying to work out. We can transform anything, we can play with any part of the circuit. The only thing we must not do is touch this. This must remain as it is throughout. So it's easier to start from the flanks, from the ends really. And we see that here we can start from here because we don't really want to tamper with that one. So we can start from here. And here we see that the 50 and the 10 kilo, those are in series. That's a voltage and a resistor. And if you recall, it means that we can transform this into what? Transform it into what again? a current source in parallel with the same resistor. So we're now going to have a current source here. Now notice that polarity, the current source must face the same orientation as the source, the voltage source. So the current source must be feeding up. The resistor will come here. It's the same resistor, so 10 kilo. But what will be the current? The current value will be, remember, voltage, Ohm's law, it will be voltage 50 over the resistance. But don't forget the resistance comes with a kilo. So this is going to be 10,000 ohms. This will go with that. This becomes 5 divided by 1000. So this is just going to be 5 milliamps or 0.0005 or 0.005. Something like that. So whichever you're comfortable with, I'll use the milli. Okay, we're now here. Now, what else? What happens here? Well, here you quickly see one thing. You see, we want everything else, all this, to be swallowed into a few simpler things that we can easily analyze. So what comes next? Now you see that these two resistors can be related. So for those two resistors, what can we say about them? They are parallel to each other. So because they are parallel to each other, we can combine them. Since they are parallel, we'll multiply them, 10 by 15. Then we'll divide by their sum, 10 plus 15. So what will be the solution here? So that combines to give us a 6 kilo ohms. So we draw our circuit so that instead of having those two, we'll put a 6 kilo here. Notice that our circuit keeps reducing. It doesn't look like we've done much, but we have made a bit of progress. So from here now, what do we do? Again, we have to transform. What do we transform? Here we're going to transform these two again. But now we'll transform them back to a voltage and a resistor. What would change in that case? We need to find what the voltage supply will be in this case. Voltage is equals to current times resistance. The current is 5 milliohms. So basically 5 milliamps by 6 kilo ohms. The milli and the kilo will oppose each other, so they'll basically just disappear out. And then the 5 and the 6 will give us a 30 volts. So that now we're drawing this. It becomes, can I squeeze it here? So I'll remove this, change this to a voltage, maintain polarity, 30 volts, and the voltage will be in series with the voltage source. Not the voltage, the resistance will be in series here. Same resistance value, 6 kilo ohms. But what do we observe now? If you can make the observation, you will understand why I had to transform it back. What do we observe here? Something reduces. What reduces?
The circuit.
these two. Those two are in series. Because of that, we can add them up. So when those two are combined, 6 and 6, we get 9 kilo. Other than that, something else also happens. You see, the current that will be passing in this line from here all the way up to here, it's the same current. So we can argue that not only is the 9 and the 30 in series, but they are also in series with this 6 that is here. So these three elements are in series with each other. Therefore, we might as well just add the 6 and the 9, making them into one element. Our circuit in that way would reduce further. So that now we can view it as this becomes 15 kilo ohms. Our circuit has reduced. Keeps becoming simpler and simpler. Now we are here. For us to make any progress, what do? We need to transform again. You see, you want the sources to speak the same language. We are going to merge even the sources as we keep doing this. Even the sources must be combined to just one source. But for you to merge the sources, they must either be both power sources or voltage sources, or they must all be current sources. Current sources are easier. So I'll transform this into a current source as well. To make the transformation, the current source will be equal to the voltage divided by the resistance. Remember 15 kilo, that has 15,000. So this is basically going to be 15 into 30, that's going to be 2. And then the kilo will mean this is going to be milliamps. Then we draw the circuit now. So in place of the voltage, we'll put the current. In place of series, we'll make this parallel. So this is now 2 milliamps. And this is 15 kilo ohms. We're now here. Now, what we observe, these three elements are all in parallel. We can simplify from here, but I want it to be obvious. Being parallel, it means that I can switch them up, as in I can change the order and it will still be the same. I couldn't do it when the circuit looked like this. Why? Because we had this and this, which meant that this and this were not parallel. They were not affecting or contributing to the same nodes. But after transforming a few times, now I've reached a point where the 2 amps is adding to that node, which is basically this node. The 1 amp is affecting this node. The two are now parallel, meaning I can just reorder them and it will still be the same. So I can redraw my circuit such that Now this can move a little bit this side. This can move this side. It's still the same thing. I haven't made anything, I haven't changed anything here. The circuit remains the same. How on earth am I going to copy this? Do it bit by bit. Now I did this for one simple reason. We could have done the following step even without reshuffling them. But what you have to just see is that these two sources are contributing to the nodes on top. First, since we're taking, according to this, we're taking up to be positive, down to be negative. We're seeing that the 2 amps is feeding to the upper node. So we'll be adding. In other words, I want to change my circuit. Let me get this one here. I want to transform it one more time. But now I want to look at these two sources as just one. I want to combine them. So if I'm combining them, what will be their overall value? So I'll take up to be positive. So once I put my arrowhead like this, I'm taking up to be positive. If I point it down, then I'm taking down to be positive. Okay. Since I'm taking up to be positive, what is happening? I'm just going to sum these, but the one pointing up will be positive. The one pointing down will be negative. So this is pointing down. So you're going to have -1. When I add these, I end up getting just 1 milliamp. So when combined, these reduce to just a 1 milliamp source feeding the upper node, like that. We see that we are not yet done. We still want to make it easy for us to get I0 here, meaning we want to swallow this one up. You must present this such that you only have the line you're trying to evaluate and one resistor and one source. The problem is easier now, but we are not yet done. So to swallow this one, we're going to transform our circuit again to a voltage source. The voltage source will be equals to 1 milliamp multiplying 15 kilo ohms. This will just be equals to 15 volts. How would the circuit look like? So this changes to a voltage source, 15 volt source feeding up in series with the same resistance, 15 kilo ohms. Now these two can combine because they're now in series. When they combine, we get 20 kilo ohms. I can just do that from here. Now I think you guys get how it goes. So those will combine to 20 kilo ohms. At this point, we can take it back to a current source. The current involved will be voltage 15 divided by 20. So this will be 3/4 milliamps or 0.75. Let's transform. At this point, I think we get how it is going. It's just now just doing it for us to see how the final solution will be. So we're transforming. This goes back to the current source, and you'll see that the current source will now have to be 0.75 amps or milliamps, feeding upwards. And then the parallel resistor, or the resistor here, will be the same one, which is 20. At this point, we see that now finally we can swallow the next one, since these two are going to be parallel to each other. We already discussed that if two resistors are parallel to each other, their combination will be half of 1. Meaning that these two will reduce to just half of 1, which is 10. And there we have it, our finalized circuit after doing as many source transformations as possible. See, at this point, getting I0 becomes straightforward. We can use current division since they're parallel, and it's a current source we are sharing. I0 will be equal to, so again, to find the current that comes to this one, it's the other resistor, which is 10 kilo ohms, divided by the sum, 10 kilo ohms plus 15 kilo ohms, multiplying the current they are sharing, 0.75 milliamps. This becomes 10 kilo over 25. The units will cancel here, leaving only the units from the current. And in the end, this will be 2 over 5 by 0.75. Okay, so yes, this will be 0.3 milliamps. So that will be our I0. So the question is, how did this become 10 here, right? Okay, so we did discuss it earlier on. We said if resistors are in parallel and they have the same value, they will always reduce to half the value of 1. So 20 by 20 divided by 20 plus 20. So this will be 400 divided by 40. This and that, 4 go ones there, we get 10. So if you have two resistors which are parallel, they will always reduce to half of 1. So I think earlier on I mentioned we actually did it like this, but I just pointed it out to say that it's not something that you always have to do, so you can just take it as a shortcut to save you a lot of time.